Hi, in this video I'd like to talk about the non-octave scale, 5 equal divisions of the perfect fifth. So what we have here is a 17-tone equal tempered keyboard. 5 equal divisions of the perfect fifth as a scale can easily be thought of as a subset of 17-tone equal temperament, or at least it's very close to a subset of 17-tone equal temperament. 17-tone equal temperament's perfect fifth is somewhere around 705 cents, while an actual perfect fifth is about 702 cents, just infinitesimally less. So, I can play the scale for you. If you think about a perfect fifth in 17-tone equal temperament as being 10 of its steps, then if you divide that by 2, you get 5 of its 2 steps fitting within a fifth. So basically, I'm putting a red dot on every 2 keys on this 7-tone equal tempered keyboard to remind me which keys not to play. So this key doesn't have a red sticker on it, which means it's not part of my 5 ED perfect fifth scale. Same with this one and this one. But these ones with the red dots are completely allowed. So, what I can do as well is play the octaves of 17 to show you how that would work. But I'm going to sort of save that for the end. So, what I became interested in the scale was sort of figuring out how different it was from 17-tone equal temperament. Like, I can play these series of ascending fifths. And then here's what happens when we're in 17 instead. What happens is the stack of fifths, as it's been discussed countless times in regular temperament theory, causes the overall pitch to increase. So by the time we get to this B here, it's still called a B in 17. We have more distance than in the equal division of the perfect fifth. Here, I'll play this note and then change it. You can hear the small but subtle difference. So then with this scale, I was seeing that it was already kind of close to 17-tone equal temperament. Like, the octaves here, in 5 equal divisions of the perfect fifth, you can tell that that is not in tune, but it can also sound like a flattened octave. And the same would be true if we went up there. Let's listen to the difference between these. Here's our regular octave. So you can hear how the 5 equal division of the perfect fifth just makes that octave a little bit out of tune. Not really out of tune enough for us to not have octaves, if that makes sense. So what I wanted to do was, I wanted to change the size of the perfect fifth we were dividing so that we could have scales where the double octave is very far off, so that it really forces us to reinterpret the structure of the scale over time. So what we can do is we can look at a continuum of perfect fifths, like we would often do in other temperaments. I saw this note up here, and this note up here. This is B and D flat in 17-tone equal temperament. And I came up with a continuum of perfect fifths that made this sonority with the C and the B, or triple octave, sound here, and then another one where the triple octave sounds here. What happens is, as our perfect fifth gets flatter and flatter here, the perfect fifth we're dividing into 5 equal parts, that stack of fifths causes things to creep into a different structure, sort of over time as we're stacking them. So, if we stack perfect fifths flatter and flatter, that means that these notes here will start to eventually get so flat that this D flat will sound like a triple octave. So the way to get those fifths flat in the right way would actually be to figure out the number of cents that makes up a triple octave, which is 3,600, divided by the total number of steps you have here. I don't quite remember how many steps exactly there are here, but I use that to figure out the exact size of fifth that would give me that. Conversely, if we divide our perfect fifth into 5 equal parts, but our perfect fifth itself is sharp, that will eventually cause these notes to get sharper and sharper more quickly than these, of course, and then these notes up here will eventually go so high that our B note here will be our triple octave instead. So a flattened enough fifth will cause D flat here to be a triple octave, and a sharpened enough fifth will cause this B here to be a triple octave. So first what I'll do is I'll go through the entire continuum, just sort of from the beginning. So it turns out that the flat fifth that gives you this triple octave value is about 692 cents. A little bit more, it's a decimal. So you can definitely tell it shimmers a little bit, but it's quite acceptable as a perfect fifth. It's just maybe a little too flat to be a mean tone fifth. But anyway, with the mean tone fifth becoming flat, we get this value is the octave here. And that's totally a part of our scale. Then next on the spectrum, I have an actual mean tone fifth, so that we get a really pure major third here, but not, here of course, because that's not allowed, and here it'll sound yucky. So pure major third here, and you can hear these notes aren't the same. Then of course, this is our 5 equal divisions of the perfect fifth. Here's 17 tone equal temperament. Our perfect fifth in 17 is around 705, so just about 3 cents sharper than the just one. So now things are getting a lot more out of kilter, and we can start comparing it to this B note instead of this D flat note. Here's about a 713 cents. So you can see that's getting pretty wide, and then at 720 cents, we finally get a triple octave here at the B. So very shimmery. It sounds less out of tune than a flatter fifth, but certainly, isn't a mean tone fifth. So there you have it. And that's the situation there. Now, as a final examination here, let's cheat and actually use 17 tone equal temperament to examine the octave itself, stretching or shrinking. Now keep in mind we're going out of the 5 tone equal tempered perfect fifth scale. You can hear it fall over time. So there's that. So there you have it. Interestingly, in some of the different spectrums, I've discovered some very concordant intervals in a few spots. In the flat ear area, the 692 cent fifth area, we, of course, get fifths that are flatter. But our major thirds are still, well, they don't really bode as well as with the mean tone fifth. You can hear that in the mean tone fifth spectrum, here, the 697 cent, that it sounds a lot more in tune than the 692 one, which is noticeably too flat. A random thing I noticed with the 720 cent spectrum is that the super major thirds are a lot closer to in tune. And I guess I don't know the exact value off the top of my head. So here's how the super major third sounds. Definitely sounds noticeably better in the 720 cent than in the perfect fifth tuning. So here's my comparison here. See, although those intervals are unusual, the one in the 720 cent snaps into place. And even the 713 doesn't really manage it quite as well. And then, of course, by the time you get to 17, it's so flat that it's about 424 cents. Well, hopefully this video was interesting for you, and you learned a little bit about the spectrums of what a 5 equal division of the perfect fifth can encompass. And I'll leave those in the description so that they're pretty clear. I also became interested in this scale because Chase Jordan mentioned it in the quarterly tunings work group. So, coincidentally, I have another non-octave scale that I'm interested in that has sort of come about as the result of talking to another composer that I met at the Charlotte New Music Festival. So that is actually what happens when we divide the perfect fifth into 4 equal parts instead of 5. So, I will see you with that video next time. This has been an exploration of 5 equal divisions of the perfect fifth. I'm actually probably going to write a piece featuring dulcimer and these keyboards. Those would be the only 2 instruments needed. Maybe non-octave studies for dulcimer is what I could call it. But I definitely want to write another piece that uses more notation.